One of the most important things in science, and especially in chemistry, is learning the conventions or rules that apply. And this is a rather tricky thing and normally comes with experience. I know I spend time doing it in my class, and I'm sure other teachers do the same. When we're dealing with different types of formula, you would have already covered the idea of empirical formula, or the least ratio between the elements involved, and of course realise that all of the inorganics, in other words the metal and non-metal combinations, all are expressed in this way. When we go through to the carbon-based or longer chain ones, we actually find we use molecular formula a lot more. And as you see, the molecular formula corresponds to the actual what's actually in the compound, but it doesn't tell us how it's put together. It is good in doing this in that it tells us what's going on, and we can actually work out which group the compound belongs to, and that helps us understand the compound a bit more. We know that the bases of the hydrocarbons, in other words, the molecules only containing carbon and hydrogen, are based upon the ratio of the carbon to hydrogen atoms. And if we look, we see that in alkanes, there is double plus 2 hydrogens for every carbon. In alkenes, in other words, if we have a single pi bond put in there as well, so a double bond between 2 carbon atoms, we see that the number of hydrogens decreases, and then it becomes double the number of carbon atoms in the molecule. And finally, if we had a triple bond or an extra pi bond, we actually find that the number of hydrogens decreases further again. Many of the compounds you're going to strike in the carbon chemistry course are going to have oxygen with them, and they can either have a single bond from the oxygen to 2 other atoms, normally a carbon and a hydrogen, or a double bond between a carbon and an oxygen. And so we get the groups of alcohols, aldehydes, ketones, esters, and of course carboxylic acids. The ones with the double bonds are the latter, so aldehydes, ketones, and carboxylic acids. The ones with the single bonds tend to be the alcohols and esters. And it's more important to think about how they are packed together. So the molecular formula in this doesn't really help us too much. If we have something like C3H8O, then that corresponds to an alcohol. But which alcohol it corresponds to? Is it the primary alcohol called propanol, or will it be the secondary alcohol, propan-2-ol? Now, both have slightly different properties, so it becomes important we know which is which. And as we can see, the double bonds, or the 2 carbon, the 2 oxygens per molecule, the carboxylic acids have that, and the smells or flavourings we use a lot in our foods, the compounds called esters, also have it. So we can actually use what's in the formula to deduce, if you like, what homologous series or which compound group we're talking about. Now, a lot of textbooks and teachers will talk about what's called a condensed structural formula. So they will add the functional group will be highlighted somewhere in your compound. And this makes it much easier to actually understand which group we're talking about. So it's taking the molecular formula and adding more information to it to allow us to sort it out. Some of the common ones you'll see are these ones. In all cases, the letter R is a convention that we used to signify a chain of carbons that are attached to this thing. So we can see that in the first case, in the primary alcohol, the carbon chain attaches to a carbon at the end, and that's where the hydroxide is situated. So the primary alcohol has the hydroxide at the end of the chain. Either end is fine. However, if we put it in the centre, as shown in the second example, we can end up with a secondary alcohol. Notice that the carbon that the oxygen is attached to, the hydroxide group is attached to, also has a hydrogen attached to it. And that is typical of a secondary alcohol. If it has a methyl or another chain group hanging from it, then that would become a tertiary alcohol. The same applies to the amine structures, in other words, an NH2 instead of an OH. And we see we have a primary amine is shown with the NH2 group added to the end of the chain. Now, if we have the C double bond O added to the end of a chain, we form an aldehyde. Now, quite often the name of this will be as an al, and an al. Now, if we have the C double bond O in the centre, somewhere in the middle of the chain, we tend to form a compound called a ketone. And of course, if we have both the C double bond O, the carbonyl group, and the hydroxide group on the same carbon, we have a carboxylic acid. So you can see here that by simply adding the functional group into our formula, we can tell the reader and remind ourselves how it is going to behave.